Hello and welcome to Talking Steam, a podcast series by Spirax Sarco. We are the world's leaders in steam technology, offering the industry's most extensive range of products and services across a variety of industries. We create solutions that set the benchmark for steam-using organisations worldwide, working with you to improve productivity, save energy, and reduce waste.
Welcome to the Talking Steam podcast and the final episode of Season 1. In this episode, I'm joined by Cornelia Schenk, Regional Sales Manager from Durban in South Africa, where we will be discussing the pitfalls to watch out for when looking to recover heat energy from your visible steam plumes. Cornelius also talks me through his experiences of recovering and recycling the heat energy and water from flash steam plumes, so please stay tuned for what is an information-packed conversation. During this episode, we discuss topics that have been mentioned in previous podcasts, so if you haven't already, I urge you to go back and give them a listen. In the last episode, we spoke with Ricardo Murakami from Chile, who shared his experiences of working with a brewing and soft drinks manufacturer to reduce their visible plumes and recover the heat energy from flash steam. Ricardo explained how he implemented the theories and practices discussed in previous episodes, and also the challenges that he and his team had to overcome during this process. My guest today, Cornelia Schenk, is a mechanical engineer working for Spirax Sarco since 2011. He is responsible for a regional team of engineers focused on delivering energy and water savings in client steam and condensate systems. Cornelius is regularly involved in delivering training on topics related to steam, so is a perfect guest joining me for this episode. I'm Mike Skidmore, your host for the Talking Steam podcast, where in this series we are focusing on heat recovery opportunities at food and drink manufacturing sites. Just a quick note to say that due to the COVID pandemic, this interview was held virtually rather than face-to-face. Hey Cornelius, thanks ever so much for joining me and welcome to the podcast.
Hi Mike, how are you doing? Always good catching up with you.
Yeah, really good, thanks mate, really good. So Cornelius, a question that I have asked to every single guest so far, and for the benefit of our audience, can you please describe where you are talking to us from?
I am in South Africa, in Durban, which is on the east coast of the country.
Brilliant, and currently working from home?
Today I'm in the office, do a little bit of work from home from time to time as and when required. As is everyone, just seeing what's practical at the time.
Okay, I understand. So Cornelius, with the other guests in this podcast series, we've explored the reasons for recovering flash steam and how to go about it, how to do it. And what I'd like to explore in this conversation today is the consequences of not doing it correctly or even not doing it at all. So at the beginning of the series, I spoke about identifying the types of steam that contribute to a visible plume and how to differentiate between controllable and unavoidable losses. So from your experience, what happens if you don't identify and separate those two types of steam before implementing flash steam recovery?
Okay, so there's a few things there. So the first one that there is, or that there could be, is that if you don't split the two up and first repair your unavoidable losses, i.e. leaks, steam traps, failed open steam traps, etc., what could happen is your diagnosis of the system could be incorrect, and that could give you an incorrect return on investment. It also wouldn't really solve the actual problem, which in a case like that would be the failed steam trap, which should be the root cause and which should be the first thing that we want to sort out. And that would make it the whole system not sustainable in the end of the day. So the right way of going about it would always be to start getting the basics right. In other words, return as much condensate as possible, fix your leaks, and make sure your lagging is correct. After that, if we see there is still an opportunity for flash steam recovery, that is when we would start investigating and putting some calculation together to see what if it will be worth it for the customer or not.
Nice, a really nice, succinct summary there. But I think you get the point across really well. And Cornelius, we spoke there about the steam traps, and in a past episode, our colleague Ricardo Murakami from Chile raised a point about the need to avoid back pressure on steam traps when recovering those unavoidable losses, all that flash steam. Can you give us a little bit of insight into the rationale behind that, please?
Well, your steam trap is as much part of your steam system, particularly when it comes to temperature control, as something, for example, as your control valve, strainers, etc. As it removes condensate, if you don't remove the condensate, the risks that you run range from safety risk, health and safety risks due to increased water hammer if it's a failed closed steam trap, or very ineffective heat transfer if the trap is failed open. So in order for a steam trap to work, any steam trap to work, there needs to be a positive differential pressure. In other words, the steam pressure on the steam, or the pressure on the steam side, has to be higher than the pressure on the condensate side. If that condition doesn't exist, your trap will not remove condensate, whether it's in a controlled system and that can cause stall in a heat exchanger, or in a normal condensate removal system, it would just back up in a heat exchanger, for example, or a coil, completely reduce heat transfer, and as I said, cause a health and safety risk. So before starting to look at systems, flash recovery systems, for example, I would advise to consult a specialist, specifically someone like Spirax-Sarco, your sales engineer, survey engineer, to come through to your plant, have a look at what the system was designed to do, and if there have been any process changes or any other changes in the system, pressure changes that could affect your condensate removal system. And that is all part of getting the basics right. When we then get to energy recovery or flash recovery, there's a few ways of doing it. The two most prominent ones for us would be through either a FREMI system, flash recovery energy management equipment, or an EDC unit, which is an exhaust vapor condenser. We could also use thermocompressors if the conditions are right. So, but let's just focus on the first two. So FREMI is where we put a system in place between the boiler feed pump and the boiler that recovers the flash steam coming back from the plant at higher pressure. You can then heat up your boiler feed water to above cavitation pressure at ambient pressure and put that into your boiler at a temperature that is higher than boiling point at absolute pressure. With the EV, the problem with that one is, or not the problem, I'd say the challenge that we have is that it does induce a little bit of a back pressure onto your steam system and your condensate system, and that would make your differential pressure over the steam traps lower. If we do want to install a FREMI system, it's very important to check that your steam traps would still be able to remove the same amount of condensate at the reduced differential pressure. So it is a slightly more challenging and a slightly more technical system to install, but it really can help from an energy recovery point of view. Now, sometimes what happens is that we get plants that don't run continuously. We get plants where the condensate return system is relatively far away from the boiler house, where a FREMI system is simply not feasible, or where financials of a plant doesn't allow them to go for a slightly more expensive system like the FREMI, with all its components and designs that goes along with it. In cases like that, we can look at an EVC, which is an exhaust vapor condenser. These units would condense flash steam, typically from a vented receiver. So it depends on what the upstream pressure is, what your volume of steam would be that you can recover. So if you look at visible exhausts from condensate systems, which sometimes seem to be just gushing out steam, that is often a bit of flash steam which comes. So when condensate goes from a higher pressure to a lower pressure, to drop it down to the just below boiling point at absolute pressure, that condensate has to flash off a certain amount of steam to drop the temperature. That is very recoverable, and the advantage of something like an exhaust vent condenser is that it can recover not only the energy and pass that on to either process or makeup water. We'll get into some examples later, But it also recovers all the water that would have been lost, and particularly in countries like ours, that is something that we really work into our return on investment calculation. Drier countries, particularly in Africa, so there's certainly it's certainly worth looking at that water recovery as well. If you look at a steam system that runs on approximately 10 bar, it would lose approximately 15 to 16% flash of the volume of the steam to flash. So that goes up into the atmosphere. So that 15% of water is very valuable in places like Africa and Middle East, hotter, drier places.
Yeah, as you've explained there, flash recovery here is like any engineering problem. It's balancing that compromise. It's understanding the compromise and then choosing the right tool for the job. And
yep, 100%.
The way that you've described the EVC there is, and when we think about a classic food and beverage manufacturing site, you can quite often have a condensate return system, taking the condensate from those processes. And often when I've worked with different manufacturers, it goes back to multiple points around that site. Very rarely do you have high amounts of flash steam generating condensate from those processes going back in almost like that Goldilocks scenario, back to just one point where you can capture all of that energy in one go. And actually having a relatively simple, low-cost solution like the EVC allows you to replicate that same solution multiple times on that plant to make sure that you can capture as much of that energy and the water as possible.
Yeah, and potentially that is possible at every single condensate point, provided that we have the correct heat sinks. So in other words, we have a heat source in the flash steam, and it could be an eyesore, it could be a waste of energy, or whatever the pain is on that site at that particular moment. But we need to use it somewhere. And that brings us then obviously to heat sinks. And that's also important to realize what the customer's needs are. Is it more energy? Is it more process? There's many different examples. Basically, each system is unique to each plant, and it depends very much on distances, away from boiler houses where you can recover the energy or the condensate. It depends on which processes are close. It depends on how you can possibly store that energy. Yeah, so there's many different possibilities and many different scenarios that exist on a plant, and the best is to simply consult with your Spirax Sarco sales engineer to advise you on what the best use of that energy is, as seeing that it is, in inverted commas, free energy. It's not free, we have paid for it, and it does contribute to as part of the process costs and the production costs.
But it's energy that otherwise would have been lost.
Correct.
Yeah, understood. Okay, so Cornelius, I mean, heat sinks have been discussed a number of times throughout the various episodes of this series, and of course you touched upon it just then. When we look at a heat sink, and if it isn't so well matched to the system that it's trying to recover energy into, or recovery from, sorry, what are the consequences there? What can go wrong with that?
Well, what could happen is there's two ways that it can go wrong. You can either undersize it for not getting enough flash, or you can oversize it where you're getting too much flash. So, or recovering too much flash steam. So when you undersize a heat exchanger or a EVC to recover flash steam, thinking that there's only X amount available, but in reality what's available is X plus, you will still have some of the losses. Now, that depends on the process that you're trying to heat up. If your process that is close by your heat sink can only absorb a certain amount of energy, then you might chalk that down as a win because you've gotten what you could. So you've improved your process somewhat. But in other cases, what could happen is that you don't have enough energy, in which case you also have to possibly split part of the heat sink off and just heat up a bit of it. So in a case like that, your return on investment might not be as great, but it depends on the actual application. One of the other things that just comes to mind is how seasons affect it as well, and what the process is. For example, one of the projects that we were involved with recently was heating up oil using flash steam, and that was just to control the viscosity of the oil so that it doesn't freeze up in the lines. So what would happen is in winter, obviously the oil gets very viscous. We try to heat it up to prevent it from clogging up the pipelines. And so in winter, what would happen is we would use all the flash steam. The heat exchanger would be designed for that, and all the flash steam would be condensed, passes its energy off into the oil, and the oil system is then very easily pumped through the process. In summer, though, we're at the same area where winter you get negative temperatures, and in summer you get plus 30s degrees Celsius, obviously. You get plus 30 degrees Celsius very often. On those sort of hotter times, there is no need for the flash, and then that would just go through the EVC, which is another advantage of the EVC. In a case like that, it wouldn't cause any back pressure on your steam system or your condensate system either. So it is a very safe and effective way of doing it, even if it's just to solve a problem seasonally.
Okay, so in this case, the manufacturer you were working with was only able to recover the heat during winter time when the demand for the oil, for heating the oil, was there. But actually, during the summer period, the flash steam plume was still visible.
Yes, somewhat. There was still a little bit of flash recovered, and a little bit of that flash steam is condensed. But obviously, because your delta T, your change in temperature of the oil is now much lower, your energy requirement from the flash steam is now lower. And then the other thing to remember with these systems is that if your heat sink and your heat source are not in step, or if they're not synchronized correctly, that means that sometimes you might actually still get some flash steam if your process isn't running. And other times when your flash steam isn't there, your process might require some energy, and for those periods you might need to still use live steam. It's very important to try and match your process to the flash usage.
Yeah, of course. I think something that's really critical to reiterate off the back of that is that you won't eliminate completely those visible emissions. As you say, Cornelius, as soon as the process and the heat sink go out of step, even briefly, you won't condense all of the flash steam. But absolutely, the opportunity and the benefit is there if you can get that heat sink optimized as much as possible to the flash steam plume, to the available energy. You can significantly reduce those visible emissions and really reap the benefits from it when you are able to recycle.
Indeed, that is so. So we always try and maximize the flash. So we would try and match the flash steam losses to whatever the closest process is. But again, that really depends on the production of the plant. And again, when we do our consultation with our customers, we have those conversations with them, with the production side as well, to discuss, which processes are running to maximize the benefit that you would get from an exhaust vent condenser.
Okay. And Cornelius, do you have any other examples of heat sinks that you've used, other processes that you've managed to lose that energy into?
Sure, we've done quite a number of these things over the years. It was not necessarily just based on energy. It was based on process and productivity improvement with the added benefit of an energy saving on the back of it. So the customer issues in a lot of these cases was more around their process than it was about energy saving. Energy saving wasn't the top priority. The fact that you do have a bit of energy saving just helps get that return on investment down to pretty acceptable levels for most of these projects that we did. So I'm not going to.
So
yeah, sorry.
Oh, sorry, mate, I interjected there.
So
what you're saying is by being able to preheat the process by recovering this energy, you're actually able to see a productivity gain or a throughput gain within the manufacturing.
Yes, and I'll talk you through some of the examples that we spoke about. Just bear in mind, most of these examples that I'll go through now have very, very good returns on investment. The ROI on these were typically anywhere between 1 to 2.5 years. which I don't think is really that bad for an energy saving solution, considering that often people would install whole solar systems for their plant to just run offices, etc. And returns on investment on those are often in excess of 10 years. So, for me, the lower hanging fruits would probably be to rather look at recovering a little bit of flash energy for a relatively low cost with a much shorter payback period as well.
Of course, and some systems, subject to government grants, especially maybe more in the solar side of things. But when it comes to thermal systems and the energy projects that we're used to delivering, 2 to 3 years is a very common payback limit
Yes.
that's often imposed. So yeah, to be able to deliver a payback within 1.5 to 2 years is normally quite desirable.
Yes, and often 12 months as well. But we've had instances where we've had 12-month paybacks on these as well. And I'll just talk you through this first project. It was done on a food and beverage company as well. They're using oil in a dog food application. So the issue that they had with condensate return is that the boiler house is about half a kilometer away from where the condensate was recovered. Now, as part of the condensate recovery system, or part of the condensate recovery system was right next to the plant where they heated up oil. Now, they used to have we first supplied a turf flow heat exchange package for them to heat up the oil. And then over time, we started realizing, hang on, there's actually quite a bit of flash steam coming out of the condensate return system for the oil plant, for the dog food plant. We then did a bit of an investigation, found out that there is quite a bit of flash available. All the steam traps were working, or the majority of the steam traps were working. So the steam system itself was in relatively good health, but there was still quite a lot of visible emission losses. We then went ahead, did the calculations, figured out that, hang on, you can get about 1.2 ton an hour of flash steam here. They ran about 8 tons an hour through the heat exchanger, and that was at 9 bar. Oh, sorry, the steam flow, not through the heat exchanger. The steam flow into the plant was about 8 tons an hour at 9 bar. So that calculates about, approximately 1.2 tons per hour of flash steam. Now, this 1.2 tons per hour of flash steam was more than enough to heat the dog food or the oil going into the dog food up to the correct temperature without having to return the condensate hot and suffering all those losses, the pump losses and the radiation losses. The heat exchanger now is basically used only for startup conditions. So when they start up, they will use the turf flow heat exchange package to just get the oil up to temperature. Once it's up to temperature, all the energy is given to the oil through the flash steam recovery. So there's no additional live steam. So I think that was a really good example of where it was prohibitive to get the condensate back to the boiler house because by the time it gets there, it would probably not be that hot. And we used that flash steam immediately as it came out of the condensate recovery unit and used that to improve a process for the client.
Brilliant. So in this case, you say the boiler house, by the time it gets back to the boiler house, the condensate would be too cool. So what sort of distance were you talking about?
In this particular case, we're talking about 500 meters, half a kilometer away from each other. So it's a significant distance to pump condensate back, to just put it back in the boiler because you would have to make up more energy in the boiler as well. We are pumping it back to the boiler, the condensate, or the water part of it, but we're actually increasing the water flow going back to the boiler house as well. So more water going back into the boiler, clean, treated water, as well as less steam being used from the boiler house in the actual process.
Excellent. Great result.
Yeah, it was a pretty good project.
Fantastic. So, Cornelius, I guess wrapping it up really with this episode, do you have any advice that you would give to an employee at a food and beverage manufacturer who would be looking to reduce the visible emissions at their plant?
The starting point would be to, as I said, make sure the basics are right. Make sure we don't have any leaks. Make sure we return as much condensate as possible if practical, and make sure that all our steam traps is in good condition. Once we've done that, we can have a look at the visible emissions again, assess if it is still a particular loss or a big enough loss. If the, and if it is, we will calculate a return on investment, have the discussion with the customer and see, is a 1 year or 2 year payback good enough for you? Should we carry on with the system? And it's also not just from condensate recovery. Call us in anyway. For example, one of the projects we were also involved in was one of our customers had used an ejector to create a vacuum in their system. The ejector, they used obviously steam for the ejector, and that steam would just go up into the atmosphere. And we decided to rather use an exhaust vent condenser once again to heat up process water using that ejector steam. And because that ejector, because the EVC has very, very little back pressure, not enough to worry about from a process point of view, we sort of managed to keep process water up to 65 degrees Celsius. And it was 2-inch line, 1.5 bar pressure, 1.5 bar gauge pressure. So we estimated about 350 kilograms an hour, and we also built a new tank for the customer. This was also one of those where the customer was very worried about his process water tanks leaking and the dirt getting into it, etc. So it wasn't really great. So we replaced the tank, and as part of that project, we also put the EVC on for him. And now, again, he only has to use direct steam injection to heat up on startup. The rest of the time, we use flash steam to keep that tank nice and warm.
Brilliant. So to use a terminology, I guess, closing the loop as much as possible, keeping as much of that energy within the system, and really reaping the benefits there. So yeah, really another great example and a great bit of advice.
Yeah, and doing so safely. I think safety is obviously critically important. As I said, you don't want to induce any back pressure on your condensate system. That could cause traps to not work upstream. That could cause things like condensate-induced water hammer or poor heat transfer. And you don't want to solve one problem and create 3 other ones. So that's why you would want to call in a consultant like someone from Spirax Sarco to have a look at the entire system. It's easy to just look at a process in isolation, but it is more important, I think, to have someone with the knowledge and the skills, what to look for, how putting a energy saving system in one area, how it could affect the rest of the plant, and putting mitigating factors in place to solve it if it's required.
And just building on that topic of health and safety, the ejector that you mentioned there, I mean, I imagine that was creating quite a steam plume from the building, from the site that you were working at.
Yeah.
Where was that ejecting to? Was it to a location where a maintenance kit team could have been exposed to it if somebody was up on the roof or in that area?
No, I think the biggest risk there was just sort of falling condensing droplets. That was the biggest risk. So in this case, it wasn't, but it is certainly something to look out for. And we subsequently identified a few other areas as well, a few other customers where they have similar systems, and we are busy approaching them with that. Because we now do have a case study where it does work and it does not affect the process at all.
Brilliant. Well, a great way to end. And Cornelius, thanks ever so much. It's been a pleasure talking to you, and I really hope you can join me in an episode in a future series.
I really look forward to that. Thank you, Mike.
That was Cornelius Schenk discussing the considerations required when recovering the energy and water from flash steam plumes and the consequences if not implemented correctly. As with any flash steam recovery system, it's essential that you identify any controllable losses before looking to recover the heat energy from a plume into another process or system. If not accounted for, these can affect the return on investment for the system and also result in not meeting your expectations for the recovered energy. Cornelius also talked us through the importance of specifying the correct means of heat recovery and the impact that back pressure on steam traps can have, with potential reductions in productivity. Some systems are designed to run with back pressure, so this isn't necessarily bad, but needs to be a consideration when implementing this type of system. Finally, we discussed the considerations for a suitable heatsink, with Cornelius talking us through the decision to recover heat to the boiler house or into a local process. He also shared the outcomes of projects that he has delivered and the unique demands of the heat sinks in each of them. Well, that's it for this series of Talking Steam, where we have discussed the benefits that you can realise through recovering the flash steam plumes at your plant. I've thoroughly enjoyed the conversations over these past 6 episodes and would like to thank my guests for their contributions and also thank you, the listeners, for taking the time to listen. If you have any feedback or suggestions for future series, we would love to hear your thoughts. Please reach out to us directly by email at talking.steam@spiraxsarco.com, through the Spirax Sarco website, or you can contact me directly through LinkedIn. Thank you ever so much for listening.
Thanks for listening. We hope that you enjoyed this podcast and join us again soon. If you have any questions about the content covered in this podcast, please reach out to us or your local Spirax Sarco engineer. Watch out for future episodes coming online soon. Follow Spirax Sarco on LinkedIn and listen to get updates on new episodes.